Okay, the recording has begun. So welcome to the Data Management Best Practices class. My name is Chris Eaker, and I'm the Data Curation Librarian in Hodges Library. My role is to help you help you with data management plans and data management of data throughout your research project, and help you kind of navigate all the requirements from federal grant agencies on how to manage data and make sure that it is adequately preserved and shared as they expect. So I'm also joined today by Joy Panicabrucha-Roberts, who is the head of our cataloging and metadata department here in the libraries. She's going to join me later to speak more about metadata, which is a very important aspect of managing your research data. So today, the outline we're going to cover is just talk a little bit about why it is important to manage your research data well. Talk about data sharing and its benefits and the positive things that come along with data sharing. And then we'll get into some tips and tricks on how to minimize error when you're entering data and also manipulating data. Some quality control and quality assurance best practices to help you find errors that you may have missed and correct them. We'll also talk about some best practices for backing up your research data and just some preservation best practices. And then Joy will talk more about metadata, which is a very important part of creating data and sharing it with others. And last, we'll finish up with some data citation best practices and principles that that I would encourage you to use as well. So why is it important to manage your research data well? Well, before we begin that, let me just mention that if you have any questions, you're welcome to place them in the chat. There is a chat window. If you move your mouse down to the bottom of your screen, you should see a menu pop up, or maybe it will be at the top of your screen. But you'll see the chat window or the chat icon that you can pop in and type a question. From time to time, I will stop and check for questions if I need to answer any. And also, everyone's muted, so if you want to open or turn on your microphone to speak to me if you have a question, you're welcome to do that as well, but I've muted everybody. So back to the presentation. So why is it important to manage your research data well? You want to manage data well for yourself to keep yourself organized, and it helps you to better find your files, your data inputs, your analytic scripts, and outputs at various stages of the process. It helps to track your science processes for reproducibility and to be able to match up your outputs with exact inputs and transformations that produce them. Also, better control your versions of research data. It helps you identify easily the different versions that you have, so that you can periodically purge versions that you don't need, or also to be able to find a version to revert to if you need to. Quality control of your data, it helps to accomplish that more efficiently. And simply put, data is a valuable asset. It's expensive and it's time consuming to collect. So we want to make sure we maximize the effective use of it and the value of that asset. It's a valuable asset not only to you as a researcher, but also to the institution, UT. Continuing improving the quality of data helps data accuracy and integrity and the timeliness of the data capture and presentation and the relevance and usefulness. It also helps you to share your research data more effectively and efficiently with other researchers. And also it helps ensure sustainability and accessibility and long-term use and reuse of that data in science. So kind of in summary, if you have data that are well organized and are well documented with adequate metadata, both within the files themselves and the groups of the files, they are preserved for future reuse, and are accessible by others for reuse, and they're also accurate and valid, meaning they actually, they don't contain errors, and they describe the phenomenon that you are trying to describe. If data are all those things, then the result is you will have high quality data that's easy to share and reuse in science. The data then can be cited by other researchers, which will add credibility to you yourself, the researcher who prepared them. And overall, it saves money and advances science. So all those reasons why we want to make sure we manage data effectively. So in addition to making your life easier, one of the main goals of effective data management is to facilitate data sharing with other researchers. Grant funding agencies want to see a greater return on their investment, and seeing data collected during projects they fund get shared with other researchers lets them know that the data is having a broader impact, and it's beyond just the research data they funded. The research project they funded. It also benefits others. So let's talk a little bit about data sharing and why it's important. So why expend the extra effort to share research data? Because it benefits the public, the research sponsor that funded your research, your broader research community, and most importantly, it benefits you as a researcher as well. So how does the public benefit from shared research data? The more informed the public is, the better they are able to understand and contribute toward more effective public and personal decisions. For example, the public needs data to help with environmental and economic planning. Also, federal, state, and local policies are dependent upon good quality research data and research findings. The public can also use data to help with social choices, such as who they'll vote for, or who they want, or how they want their tax dollars to be used, and where they'll send their children to school. Also, it can help them to make personal decisions such as health choices and exercise and smoking and nutrition and things like that, and recreational options that they might have. Next, why do research sponsors encourage data sharing? Because sponsors have an obligation to maximize the value of the research dollars and the return on those dollars and that investment. So data sharing enhances the value of the research investment by enabling external reviewers to verify the project performance metrics and outcomes. And this not only increases the credibility of the data, but also spurs new research that can be built upon the initial investment and advance the science rather than duplicate those expenditures. And the scientific community as a whole also benefits from sharing among its researchers in the community. Data sharing allows researchers to build upon one another's work and to further rather than duplicate the science and other people's efforts by exploring new findings and combining findings also into meta-analyses that can't be performed when you just have an individual data set. And also in sharing data, the scientific community expands both individual perspectives and also the collective comprehension. In addition to that, access to related research enables members of the scientific community to better reproduce, compare, and assess methods and results. And scientists are also able to learn from one another and educate new researchers about the new and most current findings and significant findings within their discipline. And finally, how does the independent researcher benefit from data sharing? When scientists share their data, they gain recognition as an authoritative source, and they are respected because they have made wise use and wise investment of the research dollars they've been entrusted with. When data are exposed to the public, the feedback from the broader community, it's used to improve the quality and the presentation of that research data. Shared data also allows for a greater opportunity for data exchange with others and networking opportunities with peers, which builds connections and provides the potential for collaborations. I'm going to go now through 4 broad steps to make data shareable, and then we'll go through the nuts and bolts of executing on those 4 steps. So step 1, the more robust your metadata, the easier your data will be discovered and the more appropriately it will be used. So specifically, when you're creating metadata, be specific in regards to the geographic and time period coverage that your data are within. For example, you may want to describe the geographic constraints in city and county and zip code if it works that way. You may also want to include latitude and longitude boundaries if it would be the most appropriate way. So that's an example on how you would describe the geographic coverages. Next, use a discipline-specific metadata schema if it's possible for you to do that. For example, geographic-related research data is most appropriately described with the content standard for digital geographic metadata. And there's also an ISO standard 19115, which is a follow-up to that geographic metadata standard. Ecological metadata, or ecological data, can be described using the ecological metadata language. And then also in the biological sciences, you have a metadata language called the Darwin Core. And then lastly, in social sciences, there is a data documentation initiative metadata standard. So there's lots of different specific metadata standards that you could use. And of course, if you're interested in learning more about what they might be for your discipline, reach out to me and I'm happy to help, or I might enlist Joy's help as well to locate the most appropriate one. Furthermore, use discipline-specific themes and place names and keywords and describe any attributes such as variable names and specimen names thoroughly. And preferably if you can use a common and standard vocabulary that is well-defined and is well used within your field, that helps even more. So we call that a controlled vocabulary. So if you use words that are already defined and already understood within your discipline, it helps others understand them more readily. So that's step 1. Step 2, be sure to include archival and reference information with properly formatted data citations as for your sources and content. Whenever possible, include persistent data identifiers such as a DOI with the data citation. Now we're going to go into data citation a little more in depth later, but this is an example of a data citation from a data set from the Dryad Digital Repository. And as you can see, there's a DOI added to the end of it, which allows the data to be located very easily. And then if you actually clicked on that link, which you're obviously not able to do now, but if you took that DOI and you went to the DOI resolver, you could actually locate that exact data set that is described in that data citation. And no matter where that data set resides, if it's moved from one place to another and the DOI is updated, then you can always locate that data set. The DOI itself will not change. However, the location behind the DOI may change, but we always want to make sure we keep that information up to date. We'll go into data citation a little more in depth later on towards the end of this presentation. Step 3, be sure to have data contributors, that is, review their metadata and ensure the validity and organizational correctness. Are the processes described correctly? Are your contributions and others' contributions described adequately and represented accurately? And is your organization properly recognized? And is the funding organization properly recognized? These are all questions you want to make sure that you include and make sure that it is complete. Be sure to make sure that that your management and sponsors check everything to make sure that everything is described properly. And then lastly, once you've done all that, the last step is to make sure that your data is shareable, or it is in a place where it can be accessed. Publish your metadata in a data portal or a clearinghouse. Seek out relevant government portals and portals developed by specific communities of practice. And these, you may find discipline-specific data repositories or data portals that can house your research data. For example, the Knowledge Network for Biodiversity and the Long-Term Ecological Research Network are both biological and ecological related research data repositories. The Digital Archaeological Record is for exactly what it says. And then the Inter-University Consortium for Political and Social Research is a social science-based data repository, which is housed out of University of Michigan. It's a vast a data store of social science research data going back decades. And the nice thing about using these types of data repositories, especially the first two, the KNB and the LTER network, is that many times the metadata from those archives are harvested and it can be searched through one interface, such as the first two items, the KNB and LTR, are part of the Data One search portal network. So a researcher can go to the Data One search portal and search across it's almost 50 different data repositories now. So when your research data is in one of these repositories, it can be searched across with many other repositories as well. And then you also have the institutional repository here at UT called Trace. And this is, we're happy to house research data within Trace to make it publicly available if that's something you want to do. I always encourage people to find a discipline-specific repository first, or if that's not available, or if you don't find one that you think would work for you, then we're happy to use Trace. And Trace is a good way to meet funder mandates to make data public, or also publisher mandates, which are becoming more common these days as well. And then this re3data.org registry of research data repositories is one way that you can find a discipline-specific repository if you want to go and play around with that and search for something that you might want to use for your research data. I highly recommend it. Now, one of the most important things that you can do when managing your research data is to take steps to ensure that that data entry, processing, and analysis are done in a way to minimize errors, or at least, to minimize it. You will never completely eliminate it, but we want to minimize it, and then we'll try to find those errors that may have slipped through in the future when we go through some quality control tips, which we'll go through in a little bit. So we'll now talk of some ways to do this while you're entering data and manipulating data. The goals of data entry are to create data sets that are valid or have gone through a process to assure quality and are organized to support the use of data and for ease of archiving. Before we look at some best practices, let's just kind of talk about some examples of poor research data entry. Many researchers like to manage their data in Excel, and Excel makes it very easy to use poor data entry practices, unfortunately. Excel doesn't enforce any rules on your data entry unless you tell it to do so. So these data are entered into an Excel spreadsheet from a small mammal trapping study. Each block of the data that you see on the screen represents a different trapping period. For example, we see this block up here is for February 13th. This block over here represents data collected on March 15th. And then this block down here represents data collected on April 10th. Inconsistencies on how the data were entered for each sampling period makes the data difficult to analyze and difficult for anyone but the data collector to understand. Note that the date is listed in different places in each block. Date is a column in the first block here, but it's listed in the header in this block here, and also this block down here. And then also inconsistent date formats are also used. In one place, the date is formatted as day, month, year, or also the month dash year with the three-letter month shown. While elsewhere, it's spelled out month, day, year here, and then day, month, year here, we assume. And also the order of the columns is inconsistent. For example, here we have site, date in the first block, and site, plot in the bottom block. So these are not in the same order, site and then date, and then site and then plot. And even the columns are named differently in different blocks. For example, species is called species in the first block. And in the next block over here, it's called rodent SP. So this can be confusing. This can be confusing, for anyone to try to make sense of this research data. So, and it would also be very, very difficult to write metadata for this spreadsheet. And there are also problems with how these data were entered. The naming of the sites is also inconsistent. For instance, deep well is used in the first block versus DW in the second block, right here. And the file contains several typos as well. You have Rio Salado shown right here, and then you have Rio Salado without the A right here. And so you have different ways of spelling the same site. And when you have the different spellings for such as deep well here or DW here, you can't really filter by just deep well with a space because you have different spellings in different places. Further, in the first block of data, you see we have the weight shown here, but then you have the mean of the weight in the last row of this column. So the value for that mean, called mean 1, is in the same column as the weight for individual species. It's a bad practice to mix different types of data within the same column. A best practice is for raw data to be maintained in one file, and then calculations on that data to be executed in another file or in another tab of the same spreadsheet, and that would be fine. You also have, in this block over here, you have some textual data mixed in with numerical data in this weight column here. Presumably, this indicates that the rodent had less than 15 grams of weight, but it escaped because they weren't, it escaped, so they weren't really able to weigh it accurately. So, a statistical program will not be able to know how to deal with this type of information with data of numbers versus data with text all in the same column. And how do you calculate the mean of 12, 92, and escape less than 15? It's not possible. So to analyze all these data using statistical software and to make it much easier to understand by any other user, these data will need to be organized into a single column for each variable. Therefore, it's essential that only one type of information be entered into each column, and that spellings, codes, and formats be consistent. So here's an example of how that data set can be reorganized such that it is understood more clearly. The data are not entered into separate blocks arrayed in a single spreadsheet. They are entered into one table with columns defined by variables date, site, plot, species, weight, adult, and comments. And so they're recorded for each sampling event, and the columns have consistent types. Each column only contains numbers, dates, or text. And there are also some consistent names, codes, and formats used in each column. For instance, all the dates are in the same format, month, day, year, and there are no typos in the site column. Species are all indicated by consistent codes. Therefore, if the user wanted to sort or subset the data for the species PERO, they could easily filter the file just for that type of data. And last, also there are only numerical data in the weight column, so a statistical software program or Excel could easily calculate statistics on that column, and preparing metadata for this Excel spreadsheet would be much more straightforward than the previous example. So I want to highlight a couple of best practices when it comes to file naming and column naming, just naming overall. A best practice is in data entry is to create descriptive column names without any spaces or special characters. Sometimes statistical programs have special uses for some certain characters, so you want to avoid using special characters within your data file. For example, under the file names example here, field visit 1 underscore small mammal data underscore the date indicates that this file contains data collected during a field visit number 1, and it contains small mammal data, and it is the version of that data set dated April 11th, 2010. And we know it's April 11th rather than November 4th because this file name uses the standard ISO date format, which is always a 4-digit year, followed by a 2-digit month, followed by a 2-digit day. And this name is much more helpful than the file mammal data. Additionally, the column name up top, soil underscore temp underscore 30 centimeters, is very descriptive. You know that it indicates the temperature of the soil at a depth of 30 centimeters rather than just soil T30. We don't know what T30 means, so this is much more descriptive. And there are a lot of great things about spreadsheets, but one must always be wary of the problems that can arise when you're using them. Spreadsheets, for example, can sort one column of data independently of all others. And the data entry person for the upper spreadsheet elected to leave empty cells for site description, treat, web, plot, and quad. And it's obviously why, if you're looking at it as a person, it's easy to understand why they did that, and it doesn't cause you really any trouble because you understand that all the data underneath, for example, all the data underneath row 2 is from the same group of observations, and then we move to another group of observations here. But if someone happens to sort the data by species, then it's no longer clear which species maps to which time period. or which measurements. And this could essentially make this spreadsheet unusable, especially if you've sorted it and then saved it and you cannot revert back to the previous version. So it's always a good idea to fill in all your cells when you're using a spreadsheet for data entry. A best practice is to enter complete lines of data. No matter how many times you have to enter that data, you want to enter complete lines so that the data are sorted in one column without loss of information. And when you collect data, you're bound to have some data points with no values. And there are ways to ensure that those values are consistent and don't throw off your analysis. One preferred way to identify missing data is to leave an empty field. But if for some reason an empty cell is not possible, for example, maybe the software you're using requires something to be in there, then you want to use an impossible value such as 9999 to indicate that this value was missing. So when you run your analysis, you can exclude specific values. And then if you need to explain something about particular data entry points, you can use data flags in a separate column to qualify empty cells. For example, in this example, you see this is a spreadsheet full of stream chemistry data. So the flag M1 on that third observation indicates that the sample was not collected at that time interval. And then also the flag E1 indicates that the value was an estimated sample, an estimated value. So when you create your spreadsheet, you would have these data flags in their own column, and then within your metadata file, which could simply be a README file that accompanies this spreadsheet, you would define what M1 means and what E1 means. So this is how you describe your content using metadata. Excel is very popular data entry. A lot of researchers use it. It allows you to enforce data validation rules. But this is something that that Excel must be told to do. It doesn't do it automatically. So for example, here you see a drop-down list has been generated that allows the user to only select specific defined entries from a list. And in this way, only defined species codes get entered and the data is consistent. This will cut down on typos when you're having to repeatedly enter the same type of data on multiple different rows. If you just go ahead and take the time up front to define that list, then you can select that from that list in a drop-down menu every time. And to do that, you use the data validation tool, and you choose the list type, and you would define a series of cells somewhere else in your spreadsheet that defines that list. And then every time you come to needing to enter that species, you just pull down and select the species from that list. So that's one type of data validation tool that Excel provides for you. Here's another example. In this example, the height variable has been defined to contain values only between a minimum of 11 and a maximum of 15. So you see here that if someone tries to enter the value 20, then because this cell has been defined to only accept numbers, integers, that is, or decimals, it would allow decimals between 11 and 15. They get this error message that you have entered an illegal value. And again, these are tools that you can use within Excel to kind of help make your life easier when entering data, and also to ensure that incorrect data does not get entered. Some researchers turn to database softwares instead of spreadsheets for their data management needs. Databases are a powerful option for storing and manipulating the data sets. And here we list some of the pros and cons of spreadsheets versus databases, which some database software packages include Oracle and MySQL, Microsoft Access. Spreadsheets are really good at making charts and graphs, and they're very powerful for calculating, and they're also very easy to use. Most people are very familiar with how to use a spreadsheet, and Microsoft Excel is probably the most predominant one. But what I always say is, yes, Excel spreadsheets are easy to use, but what they really make easy is making a poor quality data set. They lack record integrity. You can sort columns independently. They don't really enforce any rules on you unless you force it to enforce rules. Databases, on the other hand, work well with very high volumes of research data, and they're much easier to query in order to select data having particular characteristics. They also maintain data integrity. That is, one column cannot be sorted independently of others. And you also can enforce data types on databases, which is a best practice. This means that only data of type text, for example, can be entered into a column of type text, or data types numbers can only be entered within a cell that is designed to contain numbers. And this helps to prevent data entry errors. Databases do, however, have a steeper learning curve than a spreadsheet, but there are many benefits, so I encourage you to learn more about databases if you are interested in using them for your data. And I'm going to go a little more in depth into relational databases here, so you can kind of understand how they work if you haven't used them already, and to see how this might make your life easier as a researcher. A relational database matches data stored in tables by using common characteristics found within the data set. And this helps preserve data integrity and also makes it possible to flexibly mix and match data in order to get different combinations of information. A database consists of a set of tables, and each table has a defined relationship with another table or other tables using a common piece of information, which is called the primary key. And databases also have a very powerful command language for querying and for manipulating information within them, called structured query language, or SQL. And in this example, a data set for plant phenology has been divided into 3 tables. One table describes the site information, and one describes the characteristics of each sample, and then the third one describes the plant species found. And so relational databases are currently the predominant choice when storing data like financial records and medical records, personal information, and also manufacturing and logistics information. But it can be a very powerful tool to use for any type of research data set as well, as shown here in this plant phenology example. Databases feature explicit control over the data types, and they have advantages of quality control and performance as well. Here in this plant phenology table, only dates are allowed in the date column, right here. Only text is allowed within the site column, and only real numbers are allowed in the height column. And then last, if a user tries to enter, for example, a question mark where they're not sure whether the plant is flowering or not, then they're not able to do that. The database will reject that entry and say you must say yes or no, or Y or N, example. And so this is useful in defining how data is to be entered, and it eliminates the possibility of putting in the wrong type of information, like you can do very easily in Excel. Relationships can also be defined between 2 sets of data, or in this example, between 2 tables within the relational database. Suppose that you have 2 tables used in the plant phenology study, one for observations and one for sites. And so you want a table that contains both observations and the latitude and longitude of your sites. And because both tables contain a a similar piece of information called this, in this case, the site, which is the primary key, then they can be joined, like in this bottom example. They can be joined into one table that contains all the information that you want. And database features also include a powerful command language called SQL, or Structured Query Language, which I mentioned already. These are just a couple of examples of what you can do with SQL. The table at the top of this slide is called soil temp in the database. And the first example, the SQL command returns all records collected on February 1st of 2010. So the actual SQL code would be something very similar to select date, plot, treatment, sensor depth, soil temperature. This is essentially everything from the above table, from the soil temp table, where the date equals this. And so it returns it in this table here, and it brings back two entries where the date equals February 1st, 2010. And then the second statement down here, this select statement, this returns all records, which is the star, from the soil temp table, where the treatment is in and the sensor depth is 0. So from this example, you can get a sense of how easy it is to use SQL, that is to subset data from other tables based on very specific criteria. And then you can run additional analyses on the subset of data that you pull out of the larger data table. And this is very, very simple SQL. There's much more that can be done with it, but this is just to kind of explain and demonstrate what is possible. Forms can also be created within your spreadsheet, or your database, that make entering data within that database as easy as entering it into Excel, and probably easier. The screenshot shows embedded forms that were quickly generated in Microsoft Access for adding data to the 3 tables in that database of plant phenology that we were looking at just a while ago. So just in summary, be aware of the best practices when you're designing data file structures, and choose a data entry method that allows for validation of the data when you enter it. And be sure to invest the time in learning how to use a database, especially if the data set is large and complex and kind of grows beyond the limitation or the capabilities that is of an Excel spreadsheet or any other spreadsheet format. So now you've taken steps during your data entry process to minimize the possibility of data error. But that doesn't mean that you need to stop there and assume that there are no errors. And there are other ways now to help with quality control. And so we're going to go into some of those best practices now. In general, there are 2 types of errors that you can make. First, errors of commission, which are the result of incorrect or inaccurate data being input into the data set. This may happen because of a malfunctioning instrument that produces faulty results, or data that are mistyped during entry, or any other type of problem in which you incorrectly enter data. And then contrast errors of commission with errors of omission. And these result from data or metadata where those data are metadata are not recorded, they're omitted. Situations that result in omission errors are when the data are inadequately documented, or when there's human errors during data collection or data entry, or examples include when there are anomalies in the field that also affect the data. So the remainder of this module will cover some best practices for quality control and quality assurance for the different stages of a research project. First, before data collection, You should think about defining and enforcing some standards that will be used during the project. And consider formats that will be used for the data tables or data entry forms. Also, if abbreviations or specific codes need to be used, they should be defined up front and so that everyone involved understands what they are. Measurement units should also be specified, and then also relevant metadata should be identified prior to data collection. Second, you should assign responsibility for data quality before the data collection begins. Ideally, the person responsible for ensuring the data is clean and accurate is the same person collecting the data, because that person is most educated in quality control and assurance methods, or at least is most familiar with the data, and then can be trained in quality control and assurance methods. So if that's possible for the same person to do that, then that is preferable. Consider using techniques that will help eliminate mistakes during data entry. Examples include double data entry, where non-digital data are entered, keyed in by two separate people independently. Differences in data entry can then be detected via computer programs and examined further to make sure that you've eliminated mistakes. Another way to reduce data entry error is to record yourself reading off the data and then transcribe it from the recording. You may also use a text-to-speech program that reads the data to you while you type it into the computer. If you are using spreadsheets or databases, you should carefully consider how they are designed before you start entering data. And then while you're entering data, go back and check how things are working. And if you need to revise your data design, you can do so early on. Use consistent terminology within the database and make sure you atomize the data. This means only one piece of information is in each cell of the spreadsheet. Multiple pieces of information embedded in a single cell will be problematic during the data analysis. For example, set up a field, if you're using a database, restrict what can be entered within that database. You know, I mentioned earlier, always set up a field to accept only data or only numbers if that is necessary to ensure data accuracy. And then in numerical and or textual fields, you can choose a maximum number of characters or a range of values that the field will accept as well, and that minimizes chances for error as well. Finally, document any changes that you make to the data. It saves time if good records of data editing are kept, since multiple users are less likely to spend time on error checking with old versions of the data. And if mistakes are made in data editing or cleaning, good data records will allow you to locate these mistakes and undo them more easily. Documenting data changes may be as simple as creating a text file to accompany the data set, or it may be involve using a scripted program for correcting errors so that each step taken is clearly documented and can easily be kind of reverted back to a previous version and executed again if needed. Once data are entered, basic quality assurance measures can be taken. First, if data are in spreadsheets or databases, be sure that they line up in their proper columns. Also, check for any missing or impossible or anomalous values. One way to check for these problems is to sort data fields and check for discrepancies. It is often also useful to perform basic statistical summaries such as means and standard deviations. If data transformation was performed for analysis, compare the statistical summaries before and after a transformation to ensure that no mistakes were made during that transformation. Another strategy for quality control after data is entered is to look for outliers. Outliers are extreme values that may or may not be correct. If you can plot your data on a graph like shown here, you'll be able to spot these outliers more easily. And the goal is not to eliminate outliers, of course, but to flag them, to go back and look to see, is this a legitimate outlier? And if so, we want to keep it, or is this an error that we want to fix? And you want to do that early on before you start running analyses so that it doesn't mess up your analysis. Another common strategy for identifying outliers is to use graphical methods such as normal probability plots and regression or scatter plots. And if the data have some geographical component like latitude and longitude coordinates, you can map those points to be ensured that those latitude and longitudes were correctly entered. This map shows an example of an error that was a result of misentering latitude data. Another method for identifying outliers is using statistics. You can look at the deviation of a value, which is the difference between the observed value and the mean of that value of that variable. And by subtracting values from the mean of the data set, the presence of outliers or faulty data points sometimes can become more apparent. So during this tutorial, we first defined several concepts important for understanding quality assurance and quality control. And this included data contamination and the types of data errors that can result in poor data quality. And then we covered best practices for quality assurance and quality control. And these strategies are designed to prevent errors from entering a data set at first, or also to identify those errors after they've been entered. And so it's important to define and enforce these quality assurance and quality control standards before you start data collection, during the data collection, and after the data collection. Moving on to the data backup section. Now you've made all your data, you've collected all your data, you've made sure you've eliminated your errors, and you've cleaned it up. And now you want to make sure that all that hard work is maintained and you don't lose that hard work. So you want to have a good backup plan. What is the difference between backups and archiving? First of all, the main difference between backups and archiving is that backups deal with data that is copied elsewhere and potentially can be overwritten again as the data change. Whereas archiving makes a record of data that is usually in its final state. When a user performs a backup, they are in essence taking a snapshot of the data at that moment in time. And this allows the user to restore the data file as needed, such as when the current version is corrupted or it's lost, or it's somehow altered beyond recognition. Backups are often used for short-term storage or the kind of a mid-term storage, depending on the user's needs and procedures. And they're usually scheduled on a regular basis. And so what regular means for you may be different from what it means for someone else. If your research project goes out and collects data once a week, then your backup plan should be on a weekly schedule. If you've got data collected in a continuous situation from an instrument 24/7, you want a much more frequent backup schedule. You just want to think about how much of this data am I willing to lose and have to recreate. And if it's not much, then you want to create a more frequent backup schedule. So archiving, on the other hand, in contrast with backups, deals more with records that are no longer in use, and it's used to create a historical snapshot of the data. This provides for preservation of the data for future needs, either by you or by someone else that you might share the research data with. And archives are usually made when a project ends, or other times during the project when it might be appropriate, such as specific project milestones. maybe you get to the end of data collection and you've got all your raw data collected before you go through and clean it and do all that. I would recommend that's a good place to archive that raw data. And then you go through the cleaning process and the data quality control process, and you clean it up. And then you've got a good clean data set to enter your data analysis phase, and that's another good place to archive your research data. So you want to do it when you have project milestones and also at the end of a project. But regardless of whether you're dealing with backups or archives, you should have multiple copies in case one or many of those versions fail. There's many reasons to perform backups, and they include to mitigate or prohibit the loss of data, which may or may not be reproducible. You want to save time, money, and productivity. So little to none of the data will have to be reproduced. Having a backup already in place means that you are prepared for when the unexpected happens, such as a human error or a disaster or computer failure. It also allows you to go back to earlier versions and see what your results were. For example, if you're creating models and use data from an earlier model to run, the most recent file you have on your computer may not have the same data as when you first created the model input, or output, that is. It provides for the ability to send older versions of files to other people if they're requested, regardless of what the current version is that you're working with. And it also may allow you to respond during times when question results were based on older versions of the files. For example, you may find that you will have to justify your results in court or to other scientists. And so by having access to these older files in your backups and archives, you may be able to respond to their requests for more information more clearly, and you may not have to go back and reproduce that data. And that limits your liability overall. And so data preservation is really a comprehensive topic, which includes things such as backups and archives. It also includes data conversion, reformatting, and data rescue. Data rescue deals directly with older files that may no longer be in a format that's easily accessible, and it will require some sort of rescuing before it can be used again. For example, if a data file format becomes obsolete, then there are some rescue procedures that can be performed on these older obsolete file formats in order to rescue the data and to access the content within those files. Data rescue becomes more and more important also as projects end. Even if data is being preserved through the lifetime of a project, often files go untouched or become orphaned, and frequently data that has not been managed properly requires some sort of data rescue to be performed so that the data isn't a total loss. So there's some best practices for preservation. So these are some of the things that I want you to consider. Data formats. It's best to use non-proprietary and standardized data formats, and this will better ensure readability in the future. Be sure to check files after you convert them, such as data and metadata files, because sometimes information or formatting loss can occur. And if you've lost information, you want to make sure you can go back and revert to an earlier version. Versioning is important. Make sure that you use some sort of naming convention, such as incremental letters or numbers, to indicate sequential versions, and that helps you keep track of file edits and revisions. Will also help you more quickly locate the correct version of a specific file should you need to do that. Also, use file names that are consistent, descriptive, and concise. Many software programs will use a generic file name as their default file output, And if you don't change it, then you're going to have a lot of very generic file names. So you want to be specific in your file naming and descriptive so you understand what they contain. If data is well preserved, then data rescue may not be necessary. With proper file naming, utilization of proper file formats, appropriate and adequate backups, and using the right media types, you may limit or even prevent the need for data rescue. And a good data management plan, which is discussed in the previous class session that I gave last Tuesday, is another very important tool in limiting the need for data rescue because it helps you plan out all of these types of things ahead of time. For example, these are some file names. The red one is a bad file name because as we've already discussed about the dates, we don't know if this is December 4th or April 12th. So use the standard ISO format for date, and that is the 4-digit year and a 2-digit month and then a 2-digit day. And if you want to get even more specific, if you need to, then you can add information on the time and even the time zones within that standardized file format. And I just saw that I have a question about standard database format. Typically the DBF format is the standardized database format, but even like for example, Microsoft Access does have the ability to export databases as XML, which can be a very good standardized format, which you can then re-import within another database package, such as Oracle or MySQL, and then it can rebuild those tables as needed based on the XML format. So DBF or XML is also a good way to export databases. You want to, a best practice when thinking about data backup is to create a backup plan. And this may be a physical document that you have, or maybe a web page, or listed in someone's job description. And regardless of how you create it, it's important to address any of the previously mentioned issues and concerns, such as who's going to be responsible for things and where the data is going to be backed up, and how often they're backed up, and things like that. For example, if you want to make sure that you specify where physically are the backups going to occur. And my rule of thumb on creating backups is that you create 3 copies of your research data files. Your first file copy will be on your physical hard drive that you're using for the research. It could be your office computer, maybe your lab computer, whatever that case may be. That's your first copy. That's called the local internal copy. And then I would recommend you create a local and external copy. And the external format, or the external media, which I recommend, would be an external hard drive, not a CD, not a DVD, not a USB drive. Use an external hard drive. And then the third copy will be your external non-local copy. And then for this, one great possibility we have here at UT is UT's Microsoft OneDrive account. So with OneDrive, as a researcher specifically, you get, I think it's standardized, you get 1 terabyte, but you can request that it be upgraded to 5 terabytes. You can also request that OIT create you a research group account or a lab account, which will come with, I believe it's 25 terabytes. So these kind of things you want to think about. Create a local and internal copy, create a local and external copy, and then create a non-local external copy. And all of this must be spelled out very clearly in your backup plan or your data management plan. And then you want to make sure you go through and review that backup plan regularly and make any changes or updates as needed. So the next section is all about metadata. And I'm going to turn it over now to my co-host, Joy, and she's going to talk about metadata. Let me see if I can transfer keyboard and mouse control to Joy. Okay, Joy, I think you're ready to go. Joy, I can't hear you. Let me make sure that you are turned on. I'm going to mute myself, and then I'm going to unmute you. You may need to unmute yourself, Joy. See if you can unmute yourself.
Hear me now? Hello? Hello? Hello, my name is Anjali Panikabut Roberts, and I'm the head of cataloging and metadata at BT Libraries. I will discuss the importance of the metadata for your data set today. Okay. So what is the metadata? The metadata is the data about data, and it is a type of data reporting. It describes the content, quality, condition, and other characteristics of a data set. So metadata record answer a few questions such as who created data, what is the content of the data, when was the data created, or where is it geographically by the latitude and longitude, and how was the data developed, what's the data collection method, or why was the data developed. That will be your research question and methodology. So metadata is...
Joy, can you turn yourself up? We've
okay.
had some comments about not being able to hear you.
Can you hear me better now? I can use the, I can. How about this? Is this better?
Yeah, that's much louder.
Okay.
Okay.
I had a headphone on earlier and it didn't seem to work, so I'm gonna take that out. Okay. So metadata really minimize the duplication of effort in the collection of expensive digital data. It helps with the sharing, data sharing, reuse of metadata analysis, and also to use for different type of metadata analysis as well. Now, what do we have for metadata? You can see that in real life. You have your music on and your MP3 will display the name of the songwriter and the singer and different title in your file. But you can also see that in nutrition facts for calorie, type of serving, and nutrition information. And I got the delay here. And you can see that in the library catalog, we have the data, metadata such as author, title, and place of the extent of the book, and the subject of the book, and where also you can locate the metadata. For your own, I'll go back to, so for your own data, you can also create your own metadata for your own works title, your data creator, where, how, and when the data were created, and the subject or keyword to describe what the data are about. Now, why do we need the metadata then for data sets? This graph illustrates a phenomenon called the information entropy, or the gradual decline of recall associated with the research. At the time of your data development of your research project, your memory is still fresh. Details about the development of the data set are still easily recalled, and this is the best time to document information about the process that you for your data collection, population, methodology, data analysis tools and process, results, and so forth. Thus, if you don't document your data collection process over time, you may lose the ability to recall these details. The general details of knowledge about the data set will also fade away. Without a metadata record, this data might be unusable, and the data set is not considered complete without a metadata record to accompany it. And with technology change, data formats may get outdated and need to be refreshed over time, and with additional data warranting versioning. Other circumstances like retirement or career change make access to the mental storage difficult or unlikely. Sometimes the loss of your data developer leads to loss of remaining information. So metadata documenting its format is, so you need to document your formats and tools for data capturing can help with the data preservation and migration over time. For the metadata standard, what is the standard? Normally, it is the metadata best practice for common terms. You need to have a shared vocabulary for human and computer to understand the definition and structure that allow for consistent metadata recording and communication. The standards are good for both computer data exchange and also for human readable information. And the use of a standard also support your search and retrieval in data management software and application. And Chris has mentioned, and I will show you later too, that it also facilitates data visualization. So what does a metadata record look like? This example is for the Federal Geographic Data Committee standard. And the example is for the North American Breeding Bird Survey that document the data profile of how many observers have been participating in this project and how many bird data collection has been for what period of time it has been collected over time. And metadata structure and element, like Chris mentioned before, do vary from one discipline to the other. For example, this is the metadata for the Pangea database for Earth and environmental science. They require a different set of metadata elements and vocabularies that are specific to the discipline. For this example, for an ocean drilling project, you will need the metadata for the expedition, the ship's name, and geocoordinate for the drilling site. Metadata are used not only to describe the data, but also for search and facet and filter, as well as for mapping and visualizing the data. In this example, again from the Pangea database, from the deep sea drilling project. This particular site is in the Red Sea. The metadata include the citation for the data, main report of where the data has been connected to, and the project and related database, the ship's name, expedition's name, the events with latitude and longitude, location in the ocean, the size of the drill's core, and the parameter or the physical properties of the rocks and sediment collected from the drill on the smear glass analysis. Some metadata are also used for search and index for the database. In this example, the rock information are standardized, the terms are standardized, but they can also be used to search for the same rock type file in the different location through the database. And for data visualization in this example, the georeference, latitude and longitude, and location metadata are used to retrieve the image of the location in the Red Sea from the Google map, as you can see in the corner of the slide here. Now that the researcher identifiers are commonly used, database or data sets such as Pangea also allow the cross-link between the database to ORCID researcher ID, as you have seen in this example for Dr. Alice Lefebvre and her ORCID ID. Creating your ORCID ID to add to your dataset, metadata, and publication would also facilitate linking and sharing of your datasets information with Element, which is the faculty evaluation portfolio at UTK, and also the funding database that we have here called Pivot. Once you create the ORCID ID and your Pivot profile for funding opportunities, anytime you update your citation in ORCID, it will also automatically update your publication information in Pivot. And more information on metadata and data visualization or mapping can be found at these different projects. The SciMap at the Smithsonian Institute has built upon mapping scientific progress over time using data visualization. The Bonner's book, Atlas of Knowledge, is also based on this project at the Smithsonian. Another program called Kato is a mapping application that you can use to visualize your data and plot them on online maps. It is popular among geospatial digital humanities, which is a specialization that one of my colleagues, Dr. David Joseph Risley at the American University in Beirut, has been using for his linguistic project. For DJ's study of linguistic landscape of Beirut, he studied and documented and analyzed how multilingualism is expressed in a written manner in public space. The LLB project brings together more than 2,000 written language samples in Arabic, English, and French from the Greater Beirut area. So each data point on the map has the metadata for the language and the script and the geolocation of the image, taken from the mobile phone with the app called Fulcrum that works with Kato mapping application. So this is another example. This map from Cornell Lab of Ornithology is based on the selected metadata for species, date, time, and place of bird observation. This map itself is this image is for the Tennessee birding hotspots for the blue herons during the month of March to May last year. So you can see that metadata can be used in many powerful ways. I hope I can convince you how important metadata is for your data sets, from documenting and archiving your own data sets for the future, for sharing the data set in your discipline's database and websites, for data visualization, for Element, which is the faculty portfolio, and for Pivot, the funding database. And that concludes my quick section on the workshop on metadata. If you have any question, please contact me anytime, and I'd be more than happy to discuss metadata for your data sets. And I turn this back to Chris. Thank you, Chris. Hi, love, I'm in the meeting. Okay, I call you.
Thank you very much, Joy. I appreciate that, and it was very helpful in understanding the benefit of metadata and the extent to which it can be used within your research. Let's see here. Okay, the last section I want to talk about briefly is data citation. And similar to citing a published book or an article within your research, you would also want to cite any data sets that you reuse within within that data, within that research. You want to provide any and all information that's necessary to identify that data set and locate where that data can be found. Right now, there are no defined standards. However, sometimes the journal in which you publish or the repository in which you archive your research data may specify some standards, or maybe the professional organization that you're a member of might also have some data citation principles. So, but there are some general best practices that I want to kind of go through and show an example of a data citation and identify the parts. This is a data citation taken from Dryad Data Repository. Dryad is a data repository that works closely with many publishers, primarily in the ecological and biological sciences, although they are expanding. And Dryad provides a place for data sets that accompany articles within those specific publishers' journals to be archived and preserved and made available along with that article. So when an article is published within these specific journals, the data must also be made publicly available within Dryad or within another suitable repository. It doesn't always have to be Dryad, although Dryad has agreements already in place with these journals. However, in the past, I have worked with a faculty member who wanted their data set to be made public within our institutional repository called Trace. And the journal, although they did have an agreement with Dryad, accepted Trace as a suitable alternative because we met the same requirements that they wanted to meet. So you see in this example, the authors of the data set, and this is really the data creators, which are similar to the author of an article. This is the date that the data set was created, 2015. And then the title of the data set is often described as data from, and then the name of the article that it is linked to. So landscape level variation and disease susceptibility, blah, 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 that is the name of the article, which is published in PLOS One. And then the data set can be found at that DOI. Okay, so that is all I have for today. And if you have any more questions, I'm happy to help to answer them. But I want to give a plug to our group of fabulous librarians and staff here in Hodges Library that, well, all of us are great, of course, but in particular, I want to point out the Scholars Collaborative, which is a group of librarians specially grouped together for more specialized digital type of research and scholarly issues. So we have Rachel Caldwell, who is our scholarly communications librarian. If you have any questions regarding what would be the best place to publish your research data or how you might be able to make use of open access journals, or if you have questions about copyright, we always encourage you to try to maintain your copyright when you publish. Talk to Rachel Caldwell because she is well versed in all these different parts of publishing. Anything regarding data, I'm your guy. Data management plans or data management consulting throughout a research project, I can help with that. Eric Arnold is our GIS specialist. So if you have any geographic components of your research, or you want to make some really cool maps using our GIS software that OIT makes available called ArcMap, then you would want to talk to Eric. And then if you have any needs for audio or video or graphics components within your research, Michelle Brandon is our media literacy librarian, and she can help with not only the research projects that you might have, but also in instructing your students if you have if you want your students to use any particular graphics or video components in their projects, then you can talk to Rachel and I'm sorry, Michelle, and she can come in and do a special class for your students. That that wraps up today's sessions on data management best practices. I really appreciate you attending today. There's my contact information there, and also Joy's contact information. If you have any questions about anything that we talked about today, please let us know. And I will hang around for another few minutes to see if there are any questions that pop up in the chat, but otherwise I'm also available via email. Thank you very much.